Hello everyone, welcome to the class of silicon photonics. Today we shall derive the mathematical equation of free spectral range of the imbalance interferometer. So we have interferometer that is called MZI, Mach Zehnder interferometer. This Mach Zehnder interferometer is a type of imbalance. So when we call an MZI as an imbalance interferometer, if its two arms are not having equal length. So this is Y branch, this is waveguide 1 having length L1, and this is waveguide 2 having length L2. This is another Y branch. So this is Y1, this is Y2. So in imbalanced MZI, we have this L1 is not is equal to L2. So that is why when light travels from input towards the output, it travels different path and hence constructive interference or destructive interference may take place because of imbalance in the length, because of the phase difference when light travels from two different unequal path. So here the difference we can write L2 minus L1 is equal to delta L. So that is the imbalance interferometer. Now in previous class we have already derived the transfer function of imbalance interferometer. So we have given that the transfer function of an imbalance MZI as is intensity of light at the output divided by intensity of light at input is equal to 1 by 2 within bracket 1 plus cos of beta, where beta is propagation constant, multiplied by delta L, bracket closed. So this is the equation 1. So we have derived this mathematical equation earlier. This is the transfer function. This gives the relationship between the output light versus input light. I output upon I input is equal to 1 by 2, 1 plus cos of beta into delta. Sorry. Now we will find the FSR. So FSR is the two consecutive destructive or constructive interference. Suppose we have this transfer function lambda versus I output upon I input or transmission curve. So the spacing between these two peaks, two consecutive peaks, is called FSR. This is FSR. Or you can write this is also an FSR, two consecutive destructive interference. FSR. So you see FSR is nothing but a delta lambda. Where this, suppose this lambda m plus 1, this is lambda m. Now moving to defining here, FSR is equal to delta lambda is equal to lambda m plus 1 minus lambda m. This is equation number 2, which we have written here, left right hand side. Now since in this transfer function, this is your phase. This is completely your phase. So this constructive interference takes place at every 2 pi. This happens at every 2 pi. So this we call a phase. So phase This is here beta delta L. So we define the phase shift in terms of the interference transfer function as phase shift in terms of the interferometers transfer function as delta is equal to this beta into delta I is equal to you can write 2 pi n divided by lambda into delta L. So this is your phase. Now phase difference, the phase difference is occurring because of this change in this beta. Two betas are traveling. So this delta is equal to delta M minus delta M plus 1 is equal to here 2 pi. So we write this equation number 3 and this is equation number 4. So now let us move to next page. Typically, there are many peaks in our spectrum that we have seen here. There are many spectrum light which are working at higher order of the interferometers. So that we can tell higher order interferometer. So many peaks are there. So that is why delta is much greater than 2 pi. And the propagation constant, of each peak in Bm and Bm plus 1. Hence, we have 2 pi, that is the phase difference, is equal to delta m minus delta m plus 1, which is further is equal to Bm delta L minus Bm plus 1 delta L. So let us write this equation number 5. And from here only, and so delta beta, which is the difference between these two, is Bm minus beta m plus 1, beta m minus beta m plus 1 is equal to 2 pi by delta L. So this we have to remember. So you can see here, delta beta is equal to 2 pi by delta L. So even in equation also, if you see the transfer equation here, we have just written 2 pi by delta L here. If we replace this beta is equal to 2 pi by delta L, so from delta L numerator and delta L denominator both will be cancelled and you will get only 2 pi, this cos 2 pi. So this will simply show that the constructive interference or destructive interference we are achieving. So this is the equation which is quite convincing. Now let us assume that this beta, which is change in the beta, is varying linearly with respect to change in the wavelength. So you see this is the equation here, FSR equation. So this side lambda, this side we have transfer function. Suppose this variation in with respect to change in the lambda and this constructive interference or destructive interference has some variation basically, which we see later on. It varies something like that linearly, and that to negative, reducing this flow. So for that, let us write equation. Next, we approximate that beta varies linearly linearly with wavelength. So it means this delta beta is equal to beta m minus beta m plus 1 approximately is equal to minus, this is negative sign, change in beta with respect to change in lambda into delta lambda. So this is what we are trying to capture this phenomena. The change in the beta is linearly with respect to change in the wavelength. Now combining these two equations, see equation number 6 and equation number 7. Both are for delta beta. Both are for delta beta. So we equate and find out the expression for this delta lambda. And delta lambda is your FSR. So we can write from here that we just equate equation number 6 and equation number 7, since both are for delta lambda. So delta beta, sorry. So we can write here minus d beta by d lambda into d lambda is equal to 2 pi by delta L. This just we have equated. Now we want to put this equation that side, only delta lambda at left hand side. So we can write now, this delta lambda is equal to minus, since here this negative side is there, so bring negative side that side. So minus 2 pi by delta L, sorry, this is delta L, into d beta by d lambda inverse. This is what is here. So we keep this delta lambda this side only. So 2 pi by delta lambda into just inverse of dB by d lambda right hand side. So this is what we have written. So this is the equation number 8. Now we find the expression for dB by d lambda. So now we have to find out this expression. What is the expression of this? So how to find? So find dB by d lambda is what? So we know beta is equal to 2 pi n by lambda, and hence rate of change of beta with respect to lambda will be written as, this is constant, 2 pi by lambda is constant, and we have to find out the dn by d lambda plus, this is the first, this is the derivation of n with respect to lambda, plus now second 2 pi n into 1 by lambda, the derivation of 1 by lambda. So it will be minus lambda minus 2. So in simplified form, we can write 2 pi by lambda square n minus dn by d lambda into lambda. So you just check from here, we take this common 2 pi by lambda square. So we have to multiply by lambda here and 2 pi by lambda square. From here we are taking the common lambda square. So we got now this expression, equation number 9. Now put this equation number 9 into equation number 8. So delta lambda is equal to minus here 2 pi by delta L. Now we write this equation. So we see here this is inverse of d by d lambda. So we have to make it reverse. So it becomes lambda square in numerator, this one, and 2 pi and minus minus will be cancelled here. So let us make it positive. And here the expression n minus lambda dn by d lambda is in the denominator. So we see 2 pi and 2 pi cancel. So delta lambda is equal to lambda square divided by here delta lambda. It should be delta L. We have taken wrong. First here. Equation number 8, we see this is delta L. So delta L into this expression and minus lambda dn by d lambda like this. And this is nothing but your group index Ng. So we can write now in simplified form. So lambda square divided by delta L multiplied by Ng. That is the group index. So final equation for FSR becomes delta lambda is equal to lambda square, that is the operating wavelength, divided by delta L, that is the difference in the arm length L1 and L2 multiplied by Ng, group index. And expression for a group index is n minus lambda at d n by d lambda. So this is the slope, negative one. So this is called group index. So group index. So FSR is equal to delta lambda is equal to lambda square, that is the operating wavelength, divided by delta L, that is the difference between two arm length, this one. So L1 and L2, high input, high output, so and multiplied by Ng, group index, which is the material property. So with this, yeah, we can write this now this is in meter unit. So if we want to express FSR in terms of frequency, so here just replace C is equal to F lambda or C is equal to mu lambda. So from here we can find out the expression of FSR in terms of the frequency. So delta nu is equal to approximately is equal to C delta lambda by lambda square minus, and which is equal to C by delta L and G. So interestingly, you see here, you need not to know the operating wavelength if we want to find out the FSR in terms of hertz. Whereas if we want to find out the FSR in terms of delta lambda, so we need to know the operating wavelength. So that is the interesting point to find, or benefit of representing FSR in terms of the frequency. So In terms of the frequency, FSR is equal to C by delta L and G. FSR in terms of wavelength, FSR in terms of lambda is equal to lambda square divided by delta L into G. So please mind it in terms of units. So this will be in meter, standard unit. So with this, we conclude today's class. Thank you for attending this class.